This video will show how to measure and extract the current gain of the active EMI filter using our demonstration board. In the previous video, we demonstrated noise attenuation performance. Now, we'll look at another characteristic using a network analyzer. Before testing and extracting the current gain, you need to prepare two things. First, in the default state, the 0 ohm resistor at RT9 is connected. But it should be removed to connect the RT9 net to the SMA port without shorting to ground. Second, on the noise source side, there's a 1NFY capacitor at the bottom. It should be removed because the current gain is measured by sensing noise on the noise source side. The noise flows through the common mode choke and current transformer. The active filter then injects the current to port 2. To ensure this, the bypassing path of the Y capacitor must be removed before test. Additionally, 0 ohm resistors should be added to RT5 through RT8 to ensure there are no issues in the current gain measurement path. This way, the noise flows through the CM choke and current transformer without disturbance. Next, port 1 represents the noise flow and should be connected to the right side. The port 2 should be connected to the bottom side of the PCB. The injected current from the current transformer transfers to the IC first, then the IC outputs and injects it. I will terminate the receiver side with a 50 ohm resistor, while a 25 ohm resistor is typical for common mode cases. In single-phase case, using 50 ohms for convenience rarely affects the current gain measurement. Now, let's start the demonstration. The current gain measurement setup is ready, and the DC supply is now off. A network analyzer measures the S parameters first. The current gain can be extracted using Z21 over Z22, which can be obtained from the S parameters. This calculation can be done with software. You can also save the S parameters and use Python or MATLAB to transform them into Z parameters. In this demonstration, the software has already calculated the values. When the DC supply is turned on, this is 100 kHz, and this is 1 MHz. The upper side shows the magnitude of the current gain on a log scale. The bottom right represents the phase on a linear scale. You can see that the active EMI filter works from 100 kHz to almost 4 MHz, maintaining around 0 decibel. This means the magnitude of the current gain is almost 1, indicating the sensed noise is injected with the same magnitude, but the direction changes. The phase of the current gain remains close to 0 degrees, from 100 kHz to around 3 MHz. Beyond a few megahertz, there is some delay due to passive components like the current transformer, injection transformer, and capacitors. This can cause a delay. As shown in the previous video, the noise attenuation performance is effective from 100 kHz to a few megahertz. The magnitude of the current gain remains around 0 decibel, and the phase stays close to 0 degrees in this frequency range. This current gain measurement demonstrates how the active EMI filter operates through current injection. This is the end of the video. Thank you.